Next, let's talk about how different data types are laid out in memory. So first off, let's think about what is an integer. We've been talking about integers, and we need to refresh our memory on these things, right? So the most fundamental data types in embedded systems are integers. Now, an integer is just a whole number. It's a counting number. There's no fractional or decimal components. It's just 0, 1, 2, or 3. And this is the mathematical definition of an integer, right? The way that we represent integers in a digital computer are using binary, right? We are familiar with this too. We just count up in binary. So what we see when we print an integer is a translation of the binary value that underlies that data type in the computer. So 000 is 0, 001 is 1, 010 is 2, 011 is 3, so on and so forth, for however many bits we have available. Now, what about negative numbers? How do we represent negative numbers in a computer? We use the 2's complement format. And here's the 2's complement format. We have our value bits, which are the lower bits of the number, and then the most significant bit of the byte or data type or whatever it is. In this case, it's a signed character because we have 7 value bits and we have 1 sign bit. And this sign bit, if it's 1, it's a negative number. If it's 0, it's a positive number. And we use the 2's complement format. So you should refresh your memory on 2's complement. We don't need to use it in this class. Just remember how it works. Given a specific size of a data type, if it's a character, it's 8 bits. If it's a short, it's 16 bits. If it's an integer, it's 32 bits, so on and so forth. We can calculate the range, which is the smallest and largest possible values that data type can store, and we can calculate the precision, which is the smallest value change that can be represented in all of the integer types, and that's int, short, char, long, so on and so forth, all the decimal types. The precision is always 1, but when we start talking about the floating point types, the precision is variable. We can increase by changing 1 bit. We can make an increase of 0.00001 or something like that. We can make smaller changes than 1. So let's look at an example here. This is how we represent a number in a computer, right? So in this particular example, we've got 1101, and this represents a integer number. It represents a value, this pattern of bits, right? So how do we calculate this? Remember that each position represents a power of 2, and we only care about the parts where the 1s are, because we're basically just taking the value at a location, multiplying it by its power, and then adding them all together. So all the zeros are going to be 0, so that doesn't do us any good. And we just start adding together these things. I like to start at the biggest one and then go backwards. So here we've got a 1 in this position, which is to 2 to the 3, which is 8, plus 1 in the 2 position, which is 4. So 8 plus 4 is 12. Then 2 to the 0, which is 1, is 13. So altogether, the value is 13. If we look at the range of this particular format, we have 8 bits here, right? And all of these lower bits, it's assigned 8 bits. So this one is the signed number, and this is the value bits, right? So if I were to count up to as big as I could positively, it would be a 0 here, and all of these would be 1s, and that would give me so we got 8 here, 2 to the 8 is 256, but we don't have that. We are missing 1 here, so the highest we can go is 127, right? Because if we can go 128 would be a 1 here and nothing else below it. So 127 would be all of these be 1s, right? So that's the highest positive number. The highest negative number is all of these 1s again, and this one being 1, right? So we get a range of, and because of the way 2's complement works, remember that we invert and then add 1. The biggest number that we can have as a negative is negative 128. So our range for any negative integer data type is positive 127 to negative 128. Our precision, the smallest value change that we can make by flipping a bit, is 1. I can change this one here, and that's the smallest change that I can make, and that's the precision of our data type. Our various data types that we commonly use are ints, which are 32 bits or 4 bytes, shorts, which are 2 bytes, so it's 16 bits, cars or characters are 8 bits, so we get 1 byte. And notice that a car or a character, or char, I usually say char, char is 8 bits, but it doesn't have to represent just a letter. It is a number just like anything, and the letters come from translation between the ASCII table and stuff like that. So letters are an illusion. Everything is a number, and the character represents 8 bits, and it's a number. We can add 1 to them and do math with them just like all the other integers, right? It just represents a smaller size. So the unsigned range, if we don't include a signed bit, we get a range from 0 to 2 to the n, however many bits there are. If it's a signed range, it's 2 to the n minus 1, negative 2 to the n minus 1, up to 2 to the n minus 1 minus 1. That's the positive range, right? So that was when we did the car, the 8 bits, the signed version of it. That's why we got 127 here, and we got 128, negative 128 there. Note that 0 counts as positive, so that's kind of where the other positive part. And the only reason why 0 counts as positive is because all zeros is a positive number. There's a 0 in the main position, and it's not negative, right? So that's why 0 counts as positive. So let's look at a code example and see what happens when we run this particular code. So here I've got a really simple program. I declare a short. This is a signed short because there's no unsigned in front of it. So it defaults to a signed representation. And remember, this is 16 bits. It's called number. I declare it as 32767 plus 1. And then I'm going to print it out. And that's all the program does. So let's look at what happens when we do this. Okay, so here's my program in Replit. I'm going to hit enter and we'll see what it spits out, right? So is that what you expected? It's kind of surprising to me, right? And the reason why is because here I've got a positive number plus a positive number, but when I print it out, it's a negative number, right? It's negative 32768, right? So what happened here? Let's look at it. So what happens is that I start out with the value 32767, and this is a 16-bit signed short format. 32767 is all ones in everything but the highest signed bit, the most significant bit, right? So this is the biggest number that we can represent in a signed number. When I add 1 to it, that adds 1 here, which is 1 plus 1 in binary. That's 1, 0. So we carry the 1, and that carry trickles all the way down here until we get a 1 in this position, right? So now I've got a negative number and all zeros following it, which is the biggest negative number that I can represent in the 2's complement format, right? And now that's the negative 32,768 that we saw, right? This is called overflow, right? It's where I get up to the largest value that I can represent in a data type. I add 1 to it, and it becomes the smallest value that I can represent in a data type. And remember, if we're using this number for anything, that disconnect between largest and now smallest, we went from a very large positive number to a very large negative number, is a big difference. And if we have a system that's relying on that number to perform some function, we've now broken it, right? So it's really important that we remember the size of our data types and the largest numbers that they can represent in order to make sure that our code is safe, that we predict and handle overflow and underflow. We can go negative too. We can go to our negative number and subtract 1, and now we'll go to the biggest positive number. So overflow and underflow are things we need to be paying attention to as we write code for systems that people depend on.